Hello and welcome to our video lecture on absolute value equations and inequalities. There are two approaches to defining the absolute value of a real number. One is called the algebraic approach, the other one is called the geometric approach. The algebraic approach goes something like this. For any real number x, we define the absolute value of x, which is denoted by x put in the middle of two bars, is defined as follows. We say the absolute value of x is x if x is greater than or equal to 0, and the opposite of x if x is less than 0. The technical term for this kind of a definition is that the absolute value of x is a piecewise function. What that means is that it is defined in one way for part of its domain and in a different way for another part of its domain. You study these in much more detail in calculus. In words, the absolute value of a real number basically is the number itself. See, absolute value of x is x. That means the number itself if this happens. What does that mean? X greater than or equal to 0. Well, the mathematical interpretation of that is that x is non-negative. A lot of times students see that and they mistakenly read it as, or not just students, a lot of people, lay people as well, and they interpret it as x being positive. Well, that would be true if we only said x is greater than 0. But when you allow the possibility of x being 0, you can no longer read this as x is positive. You have to come up with a new word, and that's exactly what non-negative is. Notice, all one word, no hyphen needed, no dot or anything like that, and it does have a mathematical meaning. It means x is either positive or 0. So remember this term, we'll be using it quite often from this point forward. And so if x is non-negative, that means it's like 0, 1, 2/3, etc. Any number that is either positive or 0. Then the absolute value of x is just itself, see? But if x is negative, see, that's how you read that. Here there is no ambiguity. You don't need to say non-positive or anything like that, because here we say x is strictly less than 0. So in other words, when x is literally negative, then the absolute value of x is its opposite. So in other words, if I take something like -3, that falls into this category, right? So the absolute value of -3 is going to be the opposite of -3, which is what? 3. So what does this do? This guarantees that the absolute value of a real number is never negative. The worst case scenario for absolute value is 0. Okay, that's the smallest possible absolute value. You cannot get smaller than that, right? So again, notice that this notation here, x greater than or equal to 0, is the symbolic way of saying x is non-negative, and x is less than 0 is the symbolic way of saying x is negative. Here we will find these absolute values using the algebraic interpretation of absolute value, or definition of absolute value. All right, so we notice that for the first one, we're taking the absolute value of 5, and 5 is of course greater than or equal to 0, right? Because 5 is non-negative, so its absolute value is going to be itself, okay? What about the absolute value of -5? Remember, the absolute value of x is the opposite of x if x happens to be negative. And here, -5 certainly qualifies, so therefore the absolute value is going to be the opposite of itself, which is going to be what? 5, exactly. How about the absolute value of 1/2? Well, where does 1/2 reside? Let me bring you that definition real quickly. So here we have the definition. Notice the absolute value of a real number x is itself if x is non-negative. Of course, 1/2 is non-negative, so its absolute value is going to be itself. So it's going to be 1/2. How about absolute value of negative 1/2? Well, which category does negative 1/2 belong to? Is it less than 0 or is it greater than or equal to 0? Of course, it's less than 0, so its absolute value is going to be the opposite of itself. So it's going to be the opposite of negative 1/2, which is 1/2. Now you should see why absolute values never become negative. It's just because of the way that absolute value is defined. What about the absolute value of 0? Well, which category does 0 belong to? Is it less than 0 or is it greater than or equal to 0? It definitely falls into this category, right? So its absolute value is going to be itself. Just like that, okay? Very simple, very fundamental. We need to make sure we understand it, okay? The geometric approach to defining absolute value is actually really simple, beautiful, and intuitive. For all real numbers x, the absolute value of x, denoted by, again, x between two bars, is defined as none but the distance between x and 0. That's all it is. We define it in terms of distance, and then the definition becomes so much simpler, okay? So, ironically enough, the most useful definition for us as to the task of solving equations and inequalities containing absolute values is in fact the geometric definition and interpretation of absolute value. And we'll be using that heavily today. So please make sure you understand this really simple but really important definition. The absolute value of any real number is the distance between that number and 0. Note that just as in the case of the algebraic definition of absolute value, it also follows from the geometric definition that the absolute value is never negative. Why? Because it's distance, and as you know, distance is also never negative. The smallest possible distance is between a number and itself, which is 0. If it's the distance between the number and any other number, no matter how close it is to it, then it won't be 0 and it'll be a positive value. So two very different sounding definitions, but completely equivalent, and they always lead to the same result when it comes to calculating absolute values. So now we're going to find the same absolute values that we found before, but this time we're going to use the geometric interpretation. So what is the absolute value of 5? Well, it's the distance between 0 and 5, right? So if we just do a quick graph for each of these with the number on it, you'll see, for example, absolute value of 5. Basically, here is 0, here is 5. So what is this distance? That's the question, right? Notice that the distance is exactly 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 units. So that's why the absolute value of 5 is also going to be 5, because it's the distance between 5 and 0. What about the absolute value of negative 5? Well, this time we're going to need the distance between negative 5 and 0. Yeah, the position of negative 5 is different from 5, but nevertheless, it is only 1, 2, 3, 4, 5 units away from 0. So once again, the distance is 5, which means therefore the absolute value of -5, which is the distance between -5 and 0, is also going to be 5. You see how nicely that works out? Exactly the same as before. In a very similar manner, of course, you can show that this is just going to be 1/2. Absolute value of -1/2 is also going to be 1/2. And the absolute value of 0, well, what is the distance between 0 and 0? Well, clearly 0. All right, so as mentioned, as we have noticed, the geometric interpretation is more intuitive, and that's the one that we're going to use to solve absolute value equations and inequalities. We'll start with absolute value equations. In our first example, we'll look at the simplest type of problem that will involve absolute values. And in this problem, we just want to solve absolute value of x equals 3. So the first thing we'll do is we'll interpret that, what exactly that means. And if you recall, the absolute value of x is the distance between x and 0. So basically, what we're looking for here is this. We're looking for, so we're seeking real numbers whose distance from 0 is exactly 3. Okay, so if we look at this number line, we'll see that 0 is right here in the middle, and if I go 1, 2, 3 units to the right, I do find a number whose distance from 0 is 3, so I'll mark that. And if I go 1, starting at 0 again, going 1, 2, 3 units in this direction, I find another number whose distance, remember, we're not talking location, we're talking distance, whose distance from 0 is also 3 units. So therefore, now I'll go ahead and interpret that. See, when you want to solve something like absolute value of x equals 3, when you go from one step to the next, you're not performing a simple arithmetic operation. You're doing an interpretation. That's an interpretation and an understanding of what absolute value means. So we say, therefore, x is either 3 or x is -3. Usually, you may see this compactified into this form. X equals plus or minus 3. Notice that normally when these two signs are indicating the sign of a number rather than an operation between two numbers, the more correct terminology is to say positive or -3. But because, you know, as you can see, plus or minus rolls off the tongue so much better, normally when we see this, we'll say plus or minus 3, keeping in mind that we're doing a little bit of diversion from the correct way of saying it, but it's very common and that's how we say it. So we can also write our solution set, and when we write the solution set, again, we can use the compact notation, but most often in more recent textbooks and math systems like MyMathLab, you'll see them split up, because the reason we do that is because when students were looking at this, they weren't actually recognizing the fact that there are two solutions here. Okay, so remember, an equation like absolute value of x equals 3, because of what it means, is going to end up with two solutions usually. So why do we say usually? Because what if we look at absolute value of x equals 0, right? So now we're looking for all the numbers. Remember, this is a new problem. It has nothing to do with this one. So if we look at if we look for all the numbers whose distance from 0 is 0, we're not going to find two numbers. We're just going to find one number, and that's 0 itself. So in this case, we would get x equals 0. So that's why we say equations of this type will usually have two solutions. But sometimes, as you can see in this case, they'll have one solution. And what if I ask you to solve this one? This is a new example. Absolute value of x equals -1, right? Remember, absolute value of a number is a distance. What is it? It's the distance between that number and 0. And as you know, distance is never negative. So if somebody asks you to solve this, this is a very quick problem, because all you do is you'll say no such real number. Therefore, remember the triangular formation of dots means therefore in mathematics. Therefore, the solution set is empty. And remember that symbol there means the empty set or the null set. All right, so usually two solutions when the right side has a positive constant. If it's 0, only one solution, and if it's negative, no solution for that kind of a problem. All right, this is a very similar problem, except it's not just the absolute value of x, which is 3, it's the absolute value of x minus 2, which is 3. So the distance between this item and 0 is 3. So the way to think about this, which makes it very simple, is just to tell yourself, look, the absolute value of some number, remember x minus 2 is some number, right? The absolute value of some number is 3, right? So what can that number be? Remember, there are only two numbers whose absolute value is 3, right? One of them is 3, and the other one is -3, right? So therefore, if the absolute value of this expression is 3, this expression has to be one of those two numbers, right? So that's exactly how we set this up. We'll say either x minus 2 is 3 or x minus 2 is -3, because those are the only numbers, real numbers, whose absolute value is 3. So if the absolute value of x minus 2 is 3, x minus 2 must be one of those two numbers. Then we just have to solve these two simple linear equations. So we get x equals 3 plus 2, so x equals 5. And here we have x equals -3 plus 2, so x equals -1, right? Now, if you want, and if you have time, you should always check it to make sure that you did it correctly. So if we check it, so let's check x equals 5 first. So we'll plug it into the original equation. So absolute value of 5 minus 2, and see if that ends up being 3. I'm going to put a question mark on top of the equal sign because I'm not claiming it, I'm checking it. We were wondering, is it? Well, here. If you go to the next step, we get absolute value of 3. We want to know if that's equal to 3. Now we know that the absolute value of 3 is indeed 3, so we end up with 3 equals 3. Notice, once I get this identity, I no longer need the question mark. So I drop it here, I put a check, meaning it worked out, and x equals 5 is indeed a solution. So now we'll do the same thing for x equals -1. So we plug -1 into the original equation. So we get absolute value of -1 minus 2. We want to know if that equals 3. Notice that that's going to be absolute value of -3 on the left side. We're checking to see if that's equal 3. That's why we have the question mark. Now we go ahead and evaluate absolute value of -3, and of course we know that the absolute value of -3 is 3, whether we think of it as the distance between -3 or 0, or we think of it as the definition of absolute value we talked about first, the more algebraic approach, which is x if x is greater than or equal to 0, and the opposite of x if x is less than 0. Of course, -3 is less than 0, so we'll have to take this interpretation and we get the opposite of -3, which is 3. So We get 3 equals 3. Now we've reached the identity we were looking for to show us that plugging in -1 makes this equation true. In other words, turns it into an identity, and therefore it checks out. So now we see that both of them are indeed solutions, and we can write our solution set as containing 5 and -1. Again, we can put it just like this. Now, order does not matter, of course. Now, a lot of times, just for the sake of all of us having the same answer, we may agree to write them in order like this. That's fine too. Both of those sets are the exact same set. So order does not matter with sets. Sets, in other words, are not ordered mathematical entities. All right, so that's how you would handle something a little bit more complex like that. One thing I would really like you to watch out for is not this common error that students make. All right, and it is this error. So when you have an absolute value statement like this, remember, you cannot treat it as if it's just x minus 2, like in this case, and go ahead and say add 2 to both sides, etc. If you do that, you're going to just get one solution and you'll miss this problem, because this is not the correct way of approaching. Think of absolute value bars like walls, okay, that you shouldn't penetrate in this way. So the only correct approach here is to go ahead and make sure that you write the problem in this manner, interpret it as two equations, and solve it properly. So make sure to never ever do that, okay? Don't ever add into an absolute value expression or subtract from it or anything like you do with normal equations of this type with no absolute values. With absolute values, the only way you're going to get rid of the absolute value is through the proper interpretation, using either this definition or the definition that says the absolute value of x equals distance between x and 0. And as we have mentioned, these two definitions are equivalent. They will result in the exact same kind of answers when you deal with absolute value. All right, so notice at each step we're making it just a little bit more complex. Here we're just bringing in a new item here that has to be dealt with first. Remember, before you interpret the absolute value using its definition, you want to isolate it. All right, so we're going to do that. We're going to isolate the absolute value. To do that, of course, we're going to add 4 to both sides. Notice that's not a problem because I'm not adding it into the absolute value. That's a number completely outside of the absolute value, so this is completely an okay operation. So now we get 4 times absolute x minus 2 is equal to 7. So now we're going to go ahead again and isolate this absolute x minus 2. So that means we're going to divide both sides by 4. And notice that here, of course, we can do that because this is like 4 times absolute x minus 2. So we can go ahead and cross cancel like so. And we end up with absolute x minus 2 equals 7/4. All right. So now we're ready to go ahead and interpret what that means, right? So the absolute value of some number, remember, think of this as just some number, is 7/4, right? So what can that number be? Remember, there are only two numbers, two real numbers whose absolute value is 7/4. One of them is 7/4 itself. The other one is negative 7/4, right? Those are the only two numbers whose absolute value is 7/4. So if the absolute value of this expression is 7/4, it must be one of these two numbers. So that's where the next two equations come from. This is the interpretation of the absolute value statement. So we say either x minus 2 is 7/4 or x minus 2 is negative 7/4. All right. So now we just need to solve these two simple linear equations. Not the simplest because they do have fractions, so we're going to go ahead and clear the fractions first. Remember, we do that by multiplying the LCD of all the denominators in the equations on both sides. And of course, when we do so, remember, we're going to have to distribute, right? So the easiest thing is just make sure each term gets multiplied by 4. And of course, we're going to do that to this equation as well. All right, so now notice that this 4 will cancel that 4, so will that one. Okay, so we end up with 4x minus 8 equals 7. And on this side, we have 4x minus 8 equals negative 7, like so. So here we get 4x equals, move the negative 8 to the other side. I can do all that now because I'm dealing with simple linear equations with no absolute values in them. And we end up with 4x equals 15. So x equals 15 over 4. Over here we have 4x equals negative 7 plus 8. So 4x equals 1. So x equals 1/4. All right, so there we have our two solutions, right? Now, you should definitely take the time to check every time that time permits. And we'll do that here real quickly. Let me go ahead and erase some of this and bring up our calculator to help us do a quick check. Okay, so we will first try x equals 15 over 4. So here we're checking. So we'll start with x equals 15 over 4. So we want to see if 4 times the absolute value of, we're going to plug in 15 over 4 for x. So 15 over 4 minus 2, and then minus 4 is equal to 3. Okay, so let's go ahead and figure out 15 over 4 minus 2. Oh, not like that. Be careful, we gotta hit the right arrow. Minus 2. All right, so of course we can put that back into fractional form if we wanted to, but we don't really need to. So we can just go 4 times absolute value of 1.75 minus 4. We want to know if that's 3. Now, what is the absolute value of 1.75? 1.75 is a non-negative number, so it's its own absolute value. So basically, now we're just going to type it in. So we want to know if 4 times 1.75 minus 4. Now, as soon as I hit that, the enter, what do I hope to see? Think about it. 3, right? And we do. Okay, so we end up with 3 equals 3. We can drop the question mark because we have verified and we're done. Okay, now we will check x equals 1/4. And again, all we have to do is plug in 1/4 for x in the original equation. You always check the original equation because remember, what are you solving? You're solving the original equation, right? You don't want to plug it into any modified version of that. So 1/4 minus 2 minus 4. We want to know if that's equal to 3. So now we're going to go ahead and type in 1/4 minus 2, and we get negative 1.75. So we have 4 times the absolute value of negative 1.75 minus 4. We want to know if that's 3. Now remember, the absolute value of negative 1.75, it's going to be its opposite, right? So it's going to be 1.75. So we're going to get 4 times 1.75 minus 4. We want to know if that's equal to 3. We've already done this calculation right here, and we know that it's 3. So we get 3 equals 3. So this checked out, and so did this. So now we can confidently write our solution set to contain 1/4 and 15/4. You could have written the 15/4 first, then the 1/4, and it would be no problem. All right, so that's how we handle a problem of this type. So it's very simple, but you should of course run through it completely on your own by writing the problem down on a blank piece of paper and just working through it without looking at all or getting any kind of help. If you can do that really smoothly with no help needed, then you're done with the problem and you can proceed to the next one. Otherwise, you could either look into your homework for more examples like it, or you could make one up. And because remember, you can always check it at the end and see if it's true or not. So anyway, I will let you take some time to go through that, and then we'll continue. All right, for our next problem, we have absolute value of 2u plus 6 equals 19. And it's going to be handled very much the same way we handled the other ones. So we have some expression whose absolute value is 19. As we know, there are only 2 real numbers whose absolute value is 19. One of them is 19 itself. The other one is negative 19. We know the absolute value of negative 19 is 19 as well. Therefore, this expression can either be 19 or negative 19. So we have 2u plus 6 equals 19, or 2u plus 6 equals negative 19. Now we just need to solve these 2 simple linear equations. So starting with this one, we have 2u equals 19 minus 6, so 2u equals 13, u equals 13/2. For this one, we have 2u equals negative 19 minus 6, so 2u equals negative 25, so u equals negative 25/2. So we will go ahead and quickly check our answers. I'll bring up a calculator. So we'll start with checking this one, the 13/2. So we want to know if the absolute value of 2 times 13/2 plus 6 equals 19. Of course, question mark because we're checking. Looks like we won't even need the calculator, so we'll put that aside for now. So let's go ahead and simplify. We realize we can get rid of those, right? So we want to know if the absolute value of 13 plus 6, which is 19, equals 19. Now the absolute value of 19 is indeed 19, so we end up with 19 equals 19, the identity we were hoping for. So it checks out. That one is a solution. Now we're going to check this one. So we want to know, remember, we always plug in for u into the original equation. So we want to know if the absolute value of 2 times negative 25/2 plus 6 if that ends up equaling to 19. Now we notice that we can cross cancel here. So basically we want to know if the absolute value of negative 25 plus 6, which is negative 19, is equal to 19. Of course we know that the absolute value of negative 19 is indeed 19, so we end up with 19 equals 19. We can drop the question mark, it checks out, so we have two solutions and we can confidently list them because we have checked both of them. So one of them is negative 25 over 2, the other one is 13 over 2. Alright, and that's how you do that one. Alright, so you should definitely be able to handle this one. Go ahead and pause the video and try this, and then come back. See if you have the same answer as we'll get together. Alright, so we'll come back. We're going to go ahead and approach this like any other one, even though there's a fraction, makes no difference. So we're going to isolate the absolute value first. So that means we'll go ahead and move this negative 2 to the other side by adding 2 to both sides. So we end up with absolute value of 4 minus 3/4 L equals 5 plus 2, which is 7. So now we have some expression whose absolute value is 7. And since the only numbers whose absolute value is 7 are 7 itself and negative 7, we know that this expression here can only be either 7 or it can be negative 7. Now we just solve these two simple linear equations. We'll go ahead and clear the fractions by multiplying both sides by 4. Remember, because we're going to distribute, every term is going to get multiplied by 4. And of course we can do the same thing on this side. So now we end up with some cancellation over here. So this will cancel that, and this 4 will cancel that 4. So carefully write down what's left. And what we have is 4 times 4, which is 16, minus 3L equals 28. Or here we have 16 minus 3L equals negative 28. So we go ahead and move the negative 3L to the other side to make it a nice positive 3L. We'll move the 28 to the left side. So 16 minus 28 is negative 12. So dividing both sides by 3 will give us negative 4. On this side, we'll do the same thing. So we get 3L on the right side, and then 16 plus 28 on the left side. So that's going to be 30 and 14, so 44 equals 3L. So we get L equals 44 over 3. Okay, so we'll go ahead and check this one quickly. So we want to know if the absolute value of 4 minus 3/4 times negative 4 minus, actually we need to close the absolute value here. And then minus 2, we want to know if that equals 5. Now, of course, here we notice that the 4's will cancel out, but the negative remains. So there's a negative 1 actually left, right? So we end up with 4, and then negative 3 times negative 1 will give us plus 3. So 4 plus 3 is 7, and the absolute value of 7 is of course 7. So we want to know 7 minus 2, is that equal to 5? Yes, 5 does equal 5. So this one checks out. It is a solution. Now we'll go ahead and do a check of 44 over 3. So we're going to substitute that for L. So we want to know if the absolute value of 4 minus 3/4 times 44 over 3 minus 2, we want to know if that equals to 5. Now we notice there is a cancellation. There's actually 2 we can cancel out, so we can cancel out these 3's. Notice that 4 also goes into itself once, but into 44 11 times, right? So we end up with the absolute value of 4 minus 11. That's the absolute value of negative 7 minus 2, and we want to know if that equals to 5. Now absolute value of negative 7 is 7. So we want to know if 7 minus 2 is equal to 5. And at this point, 7 minus 2 is 5. So we end up with the identity we were hoping for. That means that this number, 44 over 3, when substituted for L, makes this equation true. Therefore, it's a solution of the equation. So this one checks out as well. Now we can confidently write our solution set to contain negative 4 and 44 over 3. Just like that. Very simple. Always check. That way you know you've done it correctly. And then we'll proceed. So again, simple, but it has some, moves you need to make, clear fractions, etc. So extremely good practice. Make sure you, as always, copy it down on a blank sheet of paper, try it on your own, and if you can do it without a glitch, you're ready to move on to our next problem, which we'll go to now. So please pause, do that, and then we'll proceed. All right, now we want to take a look at a few special cases when it comes to these kinds of absolute value equations. And with this, we've already seen the first one, absolute value of x equals 0. Remember, that one only gives you one solution because basically you're looking for the number, real number x whose distance from 0 is 0, right? And there's only one number that satisfies that, and that's 0 itself. So this one only gives you one solution. And of course, if you plug it in, if you want to check it, that's easy. Is the absolute value of 0 equal to 0? Is the distance between 0 and 0 0? Yes. So we get 0 equals 0, so it checks out. Same thing here, except you're not going to say x equals 0. Since the absolute value of this expression is 0, then this expression must be equal to 0. So we end up with x equals 2 actually for the solution of this one. You can quickly check it. So you get absolute value of 2 minus 2. Is that equal to 0? Well, remember 2 minus 2 is 0. So is the absolute value of 0 equal to 0? Yes, in fact, that is 0, and we get 0 equals 0, so it checks out. So the solution set here will contain the number 2. This one I already gave you a hint about as well. Notice here we have absolute value of some number. We want the distance between some number and 0 to be negative 3. Well, that's impossible. We don't have negative distances, so therefore here we say no such x. Therefore, the solution set here is empty. Same goes here. The absolute value of whatever expression it is can never be negative. So therefore, here the solution set is empty as well. Here you would say no such x minus 2, which is of course indicative of the fact that there's no such x either. All right, because if there is such an x minus 2, then just add 2 and you'll get the right x value anyway, right? So in both of these cases, the solution set will be empty. All right, the final thing we want to consider is the absolute value of a equals absolute value of b case. Here we have two absolute values that are equal to each other. And we note that if the absolute value of a equals absolute value of b, then one of the following statements must be true. The only way two numbers can have the same absolute value is if they're either equal or opposites. I think if you think about that for a minute, it'll make sense to you, because look at it. We know that absolute value of 5, for example, is the same as absolute value of 5. The absolute value of negative 5, we know, of course, is equal to the absolute value of negative 5. But notice that the absolute value of 5 is also the same as absolute value of negative 5. And the absolute value of negative 5 is also equal to the absolute value of 5. These are the only possibilities, right? So notice that the only way two absolute values are equal is if the items that are inside the absolute values are either equal, such as the first two cases, or opposites, such as the last two cases. All right, so whenever we see an equation of this type, we're going to interpret it by going to this format, right? And the thing about these equations is that these equations may have what's called extraneous solutions. That's solutions that appear to work but fail to satisfy the original equation when checked. Therefore, the point is that these kinds of equations, when solved, checking is no longer optional, the way it has been for the first few problems we've been solving. Here, checking becomes mandatory, okay? And we have to check to eliminate any possible extraneous solutions. So they're also called, by the way, extraneous roots. Solutions of an equation are also called roots of the equation. So we can say extraneous solutions or extraneous roots. Okay, so here we have a problem where we can apply the fact we just learned, namely the fact that if absolute value of a equals absolute value of b, that implies that either a equals b or a equals the opposite of b. So here, if we allow 5x plus 8 to play the role of a and 5x minus 6 to play the role of b, applying this rule, we end up with either the fact that 5x plus 8 equals 5x minus 6, or 5x plus 8 equals the opposite of 5x minus 6. Remember that a is being played by 5x plus 8 and b is being played by 5x minus 6. So we get this relationship here. So we get these two simple equations that we need to solve. So on this first equation on the left side, notice that we can go ahead and get the, both sides are simple. So we can go ahead and get the x's on one side. So we'll keep this 5x on this side. We'll move this one over so it becomes negative 5x. On this side, we'll keep the negative 6. We'll bring the 8 over so it becomes minus 8. So now we end up with 0 equals negative 14. This, of course, is a contradiction. So we're not going to get any solutions out of this first equation here. So no solution from this one, right? But that doesn't mean we have no solution at all, because we still have this other equation that we need to solve, right? So here we get 5x plus 8 equals negative 5x plus 6. So moving the x's to one side, we get 5x plus 5x, and moving the constants to the right side, we get equals 6 minus 8. So we end up with 10x equals negative 2. Dividing both sides by 10. And simplifying, notice that 2 goes into 2 once, it goes into 10 5 times. So we end up with x equals, being careful not to forget the negative, negative 1/5. And of course, remember, these are mandatory check problems because of the possibility of extraneous roots. So the mandatory check will show here. So we're going to plug negative 1/5 in for x on both sides. Make sure that we end up with the same result. So we want to see if the absolute value of 5 times x, which we will replace with negative 1/5 plus 8, is equal to the absolute value of 5 times negative 1/5, which is x minus 6. Now, we'll put a question mark because remember, we're checking, we're not asserting. So now here, 5 times negative 1/5, we know that's just going to be negative 1. So we get the absolute value of negative 1 plus 8. We're checking to see if that's equal to, on this side, that's also going to be negative 1, but we'll have negative 1 minus 6. Now on the left side, we have the absolute value of 7. We want to know if that's equal to the absolute value of negative 7. And of course, we know both of those are distances from 0, and they happen to be the same distance. So on the left side, we get 7. On the right side, we also get 7. So we get an identity. So therefore, x equals negative 1/5 does satisfy the original equation. Therefore, it is a solution. So we know that our solution set contains one solution, and that is negative 1/5. So that's how you go about doing this. Make sure that whichever does end up giving you solutions, that you check it. Checking these solutions is not optional. In many equations that we've solved so far, checking has been an optional thing that you do if you have extra time. Not with these. These are mandatory check problems. I will always let you know which kinds of problems are mandatory check problems, and in those cases, checking becomes part of the solution that you provide, not an optional aspect of it. Make sure you can handle it on your own, and then we'll proceed. So here's another one. I strongly urge you to try it on your own first, because you have all the tools required to do it now, and then come and check your answer. Alright, so I hope you did that. Now we see that we can think of this expression here as a this time, and this one as b. And of course, since absolute value of a equals absolute value of b, that implies, this little arrow right here indicates in mathematics is interpreted as implies. That is an implication. Alright, so either a equals b or a equals negative b, right? So we have either 5y over 6 minus 5 is equal to y minus 7/6, or 5y over 6 minus 5 is equal to the opposite of y minus 7/6, right? Now we go ahead and solve both of these equations by clearing the fractions first, which makes it so much easier. So we'll go ahead and, because the LCD is 6 for the whole equation, we'll go ahead and multiply both sides by 6. Notice you have 2 terms here and 2 terms here, and when you multiply each side by 6, it has to get distributed, and therefore 6 gets multiplied by each of these terms. Alright, so 6 times 6 times 6 times 6. Okay, now we go see if there's any cross canceling possible. We have one here and we have one here. And of course we can do the same on the right side. We might as well kind of do one step from each. Now actually let's wait on that because we're gonna have to distribute this side first, right? So let's actually wait till we go one more step before we do that. All right, so that's better. All right, so let's go ahead and finish this, then we'll get to the other one. So we have 5y minus 30 equals 6y minus 7. All right, so solving this now, I'll go ahead and move the 5y to the other side because 6 is the larger coefficient. It's usually better to go to the side with the larger coefficient. So you have negative 30 plus 7, so we get negative 23 equals y. Okay, so there's one of our solutions, well, proposed solutions. Remember, we have to check. For this one, we're going to distribute the negative first. So 5y over 6 minus 5 equals negative y plus 7/6. Now we'll go ahead and clear the fractions by multiplying both sides by 6. Don't forget to distribute. So we cross cancel this 6 with that 6 and this 6 with that 6. All right, so we end up with 5y minus 30 equals negative 6y plus 7. Okay, so let's move the negative 6y to this side, so we get 5y plus 6y. We'll keep the 7 on the right side, move the negative 30 over, it becomes plus 30, so we get 11y equals 37. Divide both sides by 11, we get y equals 37 over 11. Now we will check both of them. So let's start with the negative 23. So we want to know if the absolute value of 5/6 times negative 23 minus 5 is going to be the same as the absolute value of negative 23 minus 7/6. Now we will use a calculator to make this much quicker because time is limited usually after all anyway. So let's do so. So we're just going to simplify the inside of each absolute value, right? So we get 5 times negative 23, that's going to be over 6, and then we're going to exit that fraction and put minus 5. All right, so we're going to hit enter and we're going to keep track of that. All right, now let me go ahead and calculate this one. So we get negative 23 minus 7/6. Now I already know that once I hit equals, I better get either this or its opposite if this is going to become a true equation, right? So, and I get exactly the same. So here we have just indicated that these two sides are actually identical because inside each of these absolute values we're going to get the exact same thing. All right, so here we can consider that to be checked. So negative 23 checks out, it's correct. For this one, we'll check this one now. So we want to know if the absolute value of 5/6 times y, which is 37 over 11 minus 5, We want to know if that's equal to the absolute value of 37 over 11. My mind was still stuck in that 5, 6. Okay, let me. All right, so 37 over 11 minus 7/6. Okay, so remember, we're going to calculate the interior parts first, and if they happen to be either equal or opposites, we're going to be okay, right? Because the absolute values will make the two sides the same anyway, right? So let's go ahead and start with this one. So 5/6 times 37 over 11. Okay, not like that, of course. I always forget to do that. So you have to watch how you put these into the calculator. All right, so 5/6 times, let me hit a fraction line first. Actually, let me start from scratch. How's that? We'll just open parentheses. We'll put 5/6. We'll get out of there, and then we'll put another parentheses, and we'll put 37 over 11. That's the cleaner way to do it. Okay, and then minus 5, and we hit enter. Now we're going to keep track of that. Now we're going to calculate this inside part of this absolute value, and as long as we get either this or its opposite, we're going to have a true statement, right? So 37 over 11 minus, I'm going to get out of the fraction, minus, too bad these calculators don't know what you mean and just take care of that for you, but that's life. All right, 7 over 6. All right, so notice we didn't get that, but we got its opposite, which is fine, because remember, the absolute value of this is in fact going to be the positive, and so is the absolute value of that. So both of those, once you take the absolute value, will become the same and will become just that number, right? This number right here. So this one is checked out as well. So now we can confidently write our solution set to contain negative 23 or 37 over 11. So both of those worked out, and we have two solutions in this case. So again, make sure you can work through this if you haven't already done so, and we'll proceed. We're going to end today's lecture with inequalities that contain absolute values in them, also known as absolute value inequalities. In order to solve absolute value inequalities, we really want to have in mind the geometric interpretation of absolute value, which is basically the distance between the number and 0. So when we read this inequality, basically we want to interpret it as the fact that we're looking for all real numbers x whose distance from 0, which is its absolute value, is less than 3. So the first thing we do is we locate what numbers have a distance of exactly 3 from 0, and that would be 3 and negative 3. So if we just go ahead and mark that, so we have these two locations, which are exactly, notice, 1, 2, 3 units to the right and 1, 2, 3 units to the left of a 0. So if we're looking for numbers whose distance from 0 is less than 3, we're obviously going to be looking at these numbers here, any number in this region between negative 3 and 0, and also between 3 and 0 in this region. So, or 0 and 3, you should say, right? So basically, all the numbers in this region from negative 3 to 3 would satisfy this inequality, meaning they have distances from 0 which are less than 3. For example, negative 1 has a distance of 1 from 0. Negative 2.99, very close to negative 3, also has a distance less than 3 from 0. And the same goes on this side. Notice 1 has a distance of 1 from 0, and 2.9999, etc., 9 bar, right? 9 forever, also has a distance less than 3 from 0. Now, if this had said less than or equal to 3, we would have made closed circles here. But since we're looking only for the numbers whose distance from 0 is less than 3, we're only going to be looking at this region. So let me graph that, and you can go ahead and graph it, then we'll compare our answers. All right, so notice that we have open circles at -3 and 3, and then the segment joining them. So here what we have graphed is all real numbers between -3 and 3. Now that we've done that, notice it's very easy to write the solution set down, because we know that the solution set is going to be, I'll write it in set builder notation first, all x belonging to R such that -3 is less than x is less than 3. Notice this is the 3-part inequality that we have seen before. And of course, if we want to write it as in interval notation, we can just say parentheses -3 comma 3. All right, and of course, remember, if this had been different, and if we had this to graph, absolute value of x is less than or equal to 3, we would have had this same graph, except the circles would have been closed or filled in, right? So to indicate that those endpoints would be included. That would be the only difference. So let me graph that. So notice the only difference is that the circles are closed, and everything else remains the same. Of course, the solution set will change to S equals, in set builder notation, all x such that -3 is less than or equal to x, less than or equal to 3. And in interval notation, it'll be bracket -3 comma 3, and then bracket. So that would be the only difference. Now remember, at this point we were finished with the original problem. Down here we're doing a new example with a slight difference, less than changing to less than or equal to. Okay, now let's look at this one on the right. All right, so remember that for this one, the interpretation was find all real numbers sometimes to make it short, we just say find all reals whose, instead of saying real numbers, find all reals whose distance from 0 is less than 3, right? In this one, notice we're looking for values, real numbers x, whose distance from 0, remember that's what this is. The absolute value of x is the distance between x and 0, and we want those numbers x whose distance from 0 is more than 3 units, right? So find all reals whose distance from 0 is greater than 3 units. Okay, so here is 0 itself. Again, just like in this case, we'll first look at what values of x are exactly 3 units away. And as you know, that would be 3 and -3, right? So if we want all the numbers whose distance from 0 is more than 3, in other words, imagine that your house is here, you're looking for friends whose homes are more than 3 miles away from your house, for example, right? Well, there would be some friends living more than 3 miles to the right of you on the road, and some friends living more than 3 miles away to the left of you. Of course, imagining you live in a very simple town which has only one street, right? So, so basically, notice that those numbers whose distance from 0 is more than 3 are going to be either here or here, right? To the left of -3 or to the right of 3. Let me clean that up. All right, so here's the cleaned up version. So basically, the solution set for this inequality will be all real numbers to the right of 3 or to the left of -3. Not including, of course, 3 or -3, because we want all the real numbers whose distance from 0 is strictly greater than 3, right? So 3 and -3 would not fall into that category. All right, so now it's very easy for us to write the solution set now that we have the graph. And with these, as I've always recommended, it's easier to actually graph it first and then write the solution set. So the solution set here is going to be, in set builder notation, all real numbers x such that, well, we're just going to describe it. We're going to say x is greater than 3, or, extremely important that you say or and you don't say and, because if you say and, that means there is no such number. So it's very important to say or x is less than -3, okay? And the way we're going to describe it in interval notation is, let's go ahead and describe this piece first. Where does this piece begin? Well, it has no beginning. How do we indicate that? By using -infinity, right? Where does it end? Well, it does end right here. So -3. Since this endpoint is not included, we put parentheses, and then together with union these numbers. So it starts at 3, this interval, this infinite interval starts at 3, and it doesn't end, so we put infinity. And that's it. That's how you write the solution set for that, okay? So what if, just like in this case, we're going to do a sub example. What if instead of absolute x greater than 3, we had absolute value of x greater than or equal to 3, right? So notice that we would basically have exactly the same graph, except since it says the distance from 0 is either greater than or equal to 3, now we'll include 3 and -3 as well, right? So go ahead and see if you can come up with the graph of what this solution set would look like, and then you'll come back and see if it agrees with the way I do it. All right, so I hope that you have this graph here. Basically, when you change absolute x greater than 3 to absolute value of x greater than or equal to 3, the only thing that's going to do is it's going to include the endpoints as well. All right, so if you want to write the solution set, the solution set in set builder notation will be all x such that x is greater than or equal to 3, or that's these numbers, or x is less than or equal to -3, okay? And in interval notation, we'll have -infinity to 3 bracket, because this time 3 is included, union, I'm sorry, that is -3. We're describing this piece first in interval notation. Union bracket 3 comma infinity, because this time 3 is included. So we put a bracket next to -3 because it is now included, and one next to 3 because that is now included. Of course, to the right of infinity or to the left of -infinity, we always put parentheses because they're not actual numbers we can include. They're numerical concepts. All right, so that is how you would handle these simple absolute value inequalities. If you understand these, the more complex ones will just be as simple to handle, because you'll just be doing a little bit of arithmetic manipulation first. Otherwise, this is the core that needs to be understood. When I first designed this lecture, I was going to do these as separate problems, but then I realized in the previous page that it was a good place to handle them, so we went ahead and did them here. So those two problems are already done. All right, so now we want to look at these two inequalities, and notice that they are simply the same problem, except in one we're using less than or equal to, in the other greater than or equal to. As we've already seen, it makes a very, very big difference whether you have one or the other. So we'll see the difference again here. Now, just as in the case of the equations that were a little bit more complex, containing absolute values, we're going to go ahead and isolate the absolute values. So here we end up with 3 times absolute 2x minus 3. We'll first add 5 to both sides. So on the other side, we get less than or equal to 7 plus 5. So 3 times the absolute value of 2x minus 3 is less than or equal to 12. So absolute value of 2x minus 3 is less than or equal to 4, because we divide both sides by 3. So now we basically think of this entire expression as just some number, right? So we're looking for some number whose distance from 0 is less than or equal to 4. We know that those numbers are going to be between -4 and 4, remember? So here we're just going to interpret this and rewrite it as -4 less than or equal to 2x minus 3 less than or equal to 4. Because those are the numbers n whose distance from 0 is less than 4. Except we replace n with what? With 2x minus 3. All right, so now this is a 3-part inequality. We know how to solve these. So we're going to go ahead and add 3 to all 3 sides first. And that will give us -1 less than or equal to 2x less than or equal to 7. And finally, we'll go ahead and divide everything by 2. So we get -1/2 less than or equal to x less than or equal to 7/2. And the easiest thing to do is to plot that solution set first and then write down what it is. It'll be that much easier if you do so. So go ahead and sketch a graph of this solution set, pause the video, see if you can do that, and then come back. All right, so the first thing you're going to want to do when you graph something like this is know the location of these two fractions. Now, -1/2 is simple because you know it's halfway between -1 and 0, so it's right there. So we can just mark that as -1/2. Now 7/2 you'll want to go ahead and convert to a mixed number by just doing a long division. So we know that we get 3 times 2 is 6, so we get 3 and 1/2, right? So you know it's going to be halfway between 3 and 4. And then of course all the numbers in between. So we want to go ahead and write the solution set. Now we can actually write the set builder version very quickly right here. We can just say S equals all x such that basically that happens, right? Now in interval notation, remember you need either parentheses or bracket depending on inclusion. In this case there is inclusion, so we start with bracket. Where does it begin? At -1/2. Where does the interval end? At 7/2 or 3.5. We're going to want to go ahead and write that as a an improper fraction. It looks nicer, okay? And just like that, okay? And we will need bracket at the end, right end as well, because that's also included. Now, notice that the case with greater than or equal to, the first part we do very similar things. So let's go ahead and isolate the absolute value term. So we get 3 times absolute 2x minus 3 greater than or equal to 7 plus 5. So 3 times absolute 2x minus 3 greater than or equal to 12. So absolute value of 2x minus 3 is greater than or equal to 4. So we're looking for real numbers. Let's just call that expression n. So we're looking for real numbers n whose distance from 0 is greater than 4. We know that the kinds of number who will satisfy that condition are the numbers that are either greater than or equal to 4 or less than or equal to negative 4, right? So here we're going to say either 2x minus 3. Let's start with the left side first. So we'll just say less than or equal to negative 4, or 2x minus 3 is greater than or equal to 4. What I always like to do for myself is I have a couple of simple examples in my mind, and then I'll use those as the model. I know that if I'm dealing, for example, with say absolute x less than 2, I know this is going to look like this. Here is 0, here is 2, here is negative 2. I know I'm going to get those numbers. And I know that if I'm dealing with absolute value of x is greater than 2, now I'm looking for numbers whose distance from 0 is greater than 2. So I'm going to be looking at the numbers here to the right of 2 or to the left of negative 2. Having this simple model in your mind, then you can apply it to different situations. So here we're dealing with a greater than or equal to scenario, so it's this version, right? So you're either going to be greater than or equal to, well, we don't have 2, we have 4 here, so either greater than or equal to 4 or less than or equal to negative 4. You could write this one first, then this one, or vice versa. Makes no big difference. I just went from left to right, okay? So here we get 2x is less than or equal to negative 4 plus 3. So 2x is less than or equal to negative 1. So x is less than or equal to negative 1 half. For this one, we get 2x is greater than or equal to 7. So x is greater than or equal to 7 halves. And remember, those are separated by an or. So let me go ahead and get rid of these real quickly now so we have more space. All right, so basically the values that we're interested in, the solution values, are x values that are either less than or equal to negative 1 half or x greater than or equal to 7 halves. In fact, if I went ahead and moved that a little bit to the right, give me 1 second. All right, so I just wanted to move it a little bit to the right so that I can actually go ahead and write it as my solution set in set builder notation. All right, but I'm going to go ahead and graph it at this point before I write the interval notation. All right, so notice that the numbers in play for our graph are once again negative 1 half and 7 halves, which is 3.5. So, but this time we want numbers less than or equal to negative 1 half, therefore the arrow to the left, or greater than or equal to 7 halves, right? So we can go ahead and write the interval notation version of the solution set, and that will be, we'll look at this piece first. It has no beginning, so we put parentheses, negative infinity, comma. It does end here at negative 1 half, and it does include negative 1 half, therefore bracket after negative 1 half. And then union, this piece, so bracket 7/2 because 7/2 is included, comma, infinity. All right, so that's that. Make sure that you can handle that comfortably, and we'll proceed. All right, we're almost done with the video, just a few special cases, and we will call it the day. So first thing we want to look at is, what about this? What if somebody says, find all real numbers whose distance from 0 is greater than or equal to -4? Well, think about it. This statement is pretty much always true, right? For any real number, if you find the distance for that real number and 0, it's going to be greater than or equal to 0. So certainly it's going to be greater than or equal to -4, right? So this one is true for all real numbers, for all x belonging to the set of real numbers, right? Just think about it. Think of some examples. 2. Is the absolute value of 2 greater than or equal to -4? Of course, the absolute value of 2 is 2, which is greater than or equal to -4. Think of 0. Is the absolute value of 0 greater than or equal to -4? Sure. 0 is the absolute value of 0, and that, of course, is greater than or equal to -4. Let's think of -2. Is the absolute value of -2 greater than or equal to -4? Sure. The absolute value of -2 is 2, which is greater than or equal to -4. Therefore, this is true for all real numbers. Sample points we picked were x equals -2, x equals 0, and x equals 2. Substitute each and you'll see that it's true, and that works with all real numbers. So the solution set basically will be -infinity to infinity. How about this one? Think about it. We're looking for real numbers x whose distance from 0 is less than or equal to a negative number. Can you think of any such real number? No, you can't, right? Because any real number is going to be having an absolute value that's greater than or equal to 0, so it certainly will never be less than or equal to -4. So this is the extreme other case. Here, the solution set is empty because there is no such x in the set of real numbers. All right? That's how you handle those special cases. Be a little bit careful with this one. Don't immediately say, oh, there is no real number who's going to have absolute value less than or equal to 0. If they said this, you could be that confident because there is no real number whose distance from 0 is less than 0. This is empty, okay? This solution set, not this one, because this one says less than or equal to 0, because this means absolute value of x is less than 0 or absolute value of x equals 0. That's what less than or equal to 0 means, right? Yes, this part, no solution, right? But this part does have a single solution, x equals 0. So be real careful with that case, okay? So you would write your solution set as containing a single point, 0, okay? So that one does have one single solution, and that's 0. This one, of course, no solution. There is no real number whose absolute value is less than 0, because that would mean it's negative. How about this one? Is this true for all real numbers? You may be thinking, yes, it actually is. For all real numbers x, the absolute value is distance and therefore greater than or equal to 0. So the solution set here is all real numbers, right? Not so fast with this one, right? For this one, it's true for all real numbers, right? Except for one number. Which one is that? If you said 0, you would be correct. So the solution set here would be all x as long as x does not equal to 0. Because remember, the absolute value of 0 is not greater than 0. The absolute value of 0 is 0. So if you want to show this using interval notation, remember, you want all real numbers to the left and to the right of 0. You just want to exclude 0, right? So we'll take care of the left piece. That's negative infinity to 0. Of course, with parentheses afterward because 0 is not included. Union, again, start at 0, but not including 0, and then toward infinity. This is how you exclude a single number from your solution set. And that is the solution set of this particular inequality. All right, so that does it for absolute value equations and inequalities. Please practice them here before you move on to the problem set, and that should do it for us. So stay safe until our next video.